In this video, I want to review a little bit about scalar and vector projections, and then I want to begin talking about cross product, what it does, and a little bit of how we find it and why it is the way it is. And then the next video will show how you actually calculate the cross product and something called the right-hand rule. Okay, so the scalar projection, we have the formulas down here. If you remember, the scalar projection is simply if you took, if I can maybe just sketch this, if you had a vector A and another vector B, and you dropped vector B onto A, 90 degrees, okay? The scalar projection, I'm going to do this a little bit of color coding. The scalar projection is the length of that green piece I just drew. And I'm going to make this a little bit maybe confusing, but the actual vector, I'm going to add this, okay, kind of a dot, are the actual components of that red vector, okay? So it's really projecting B onto A, figuring out how long that resultant vector would be, and what the components are. So, first thing, the scalar. Let's dot these two vectors. So, -3 plus -2 plus 25. So the dot product is 20 over the magnitude of A. So -1 squared plus -2 squared plus 5 squared. So let's say 1 plus 4 plus 25. So the magnitude is the square root of 30. This is my scalar, so the length of that vector. To find the projection, the actual vector, if you recall, the formula says take this answer and multiply it by the unit vector of A, which we could simplify then because the unit vector would be vector over magnitude. So that's where the magnitude squared comes. So the way to do this is you say, well, 20 over the square root of 30 squared is just 30 multiplied by vector A. Okay, so this is equal to, let me do some simplifying here, -2/3, 4/3, and 10/3. Okay. All right, the next one. Let's dot these things. So, -6 plus 0 plus -2. So -6 plus -2, my dot product is -8 over magnitude of A. 3 squared plus 2 squared plus -1 squared. So 9 plus 4 plus 1, my magnitude is the square root of 14. So I will take my -8 over 14 and multiply that, because remember you square by A. So I've got -24 over 14, which I could reduce, and -16 over 14, which I could reduce, and 8 over 14, which I could reduce. And I certainly could do that. We've got -12 over 7. We've got -8 over 7. And we've got 4 over 7. Let's begin talking about cross product, what it is, what it does. Okay, so we talked about dot product. I like this this idea, this graph, that vectors act on each other in a couple of ways. Okay, and these are all the ways. Like vector A is affected in the x direction by B, in the y direction by B, in the z direction. It's affected in the x, y, and z direction by a new vector. The dot product is how these things work together. How is x affected by x? How is y affected by y? And how is z affected by z? That's the dot product. And that's why we add those resultant forces up. The x is multiplied, the y is multiplied, the z is multiplied. That is a scalar that says how are these vectors working together in their directions. The cross product maybe is the rest. It's how is the x component in the first vector being affected by the y and z of the second vector? How is the y component being affected by x and z? And how is the z being affected by x and y? So all the interactions are the dot products, similar parts, and the cross products, different parts. The cross product will give you a new vector. Okay, and I'll explain that in just a minute with a different picture. But the dot product gives a scalar, a number, and the cross product gives a new vector. The cross product's resultant vector, the new vector, will be orthogonal to the original vectors. Now, I put down here, see the proof. The proof is too long to go over in this video, but essentially the cross product is set up so that, let's say I have two vectors, and I'm going to name them just like A, B, and C. That's vector 1, and vector 2 will be D, E, and F. Essentially, you have this new vector. I'm going to call it like X, Y, and Z. And we set it up so that if I dot A, or the first vector with the red vector, I get 0. And if I cross this vector with the red vector, I get 0. So I want to create a new vector that is orthogonal to the original two vectors, both of them. And if that sounds like a lot of algebra, it is. It's not hard algebra because all you're trying to do is solve for unknowns. You know, what could I do with this to dot it with that and get 0? And what would this have to be to dot to give 0? So it's essentially two equations with three unknowns each, and you do the algebra to make it work. So let me explain cross product a little bit different way with this picture. The dot product says, let's say you're boating with the current and the current is pushing you. That's what dot product is trying to find. It's trying to find out what is this combined momentum. How is the new vector strengthening the vector I already have? Okay, and that's what we've already talked about. We get this scalar. But the cross product says, let's say and I like that it's crossing the river here, you've got a current. How is the current affecting you? So obviously, if you think about moving this way, you are being pushed in the other direction by something. And what you're being pushed by, we could find using the sign. If you think about drawing on this, you know, we're saying, well, you're being pushed this way. How much? Well, of course, it's the opposite and hypotenuse. We know the force working on the hypotenuse, and we want to know the opposite. That's why dot product, remember, deals with law of cosines. Cross product deals with sines because we're looking for this opposite force that's happening. Okay? And we know the hypotenuse, we know the current. We want to know how is that working here. So the cross product says, how are the opposites pushing our vector? Okay? So calculating the cross product, there are a number of ways to do it. This method right here is maybe more of a physics method where you're told how some forces or what some forces are and the angle that they're working at each other, and you can then calculate a resultant force. This is the official formula that comes from that proof I described, where you would say I have two vectors, A and vector B, and I am finding a new vector that will dot with each one separately to give 0. And at the end of the proof, you get this formula right here. This is a hard formula to memorize, so I choose to organize it. This is my favorite way to do it, in a matrix. And I'm going to show in the next video how we can use this matrix to calculate our cross product. Again, this is really organizational, okay? I'll explain how this matrix works, but the matrix is not a proof, and the matrix is not a It's not like a way of proving anything. It is simply a way of calculating. It's an organizational tool for calculating. The proof yields this formula right here. The proof that says I dot A with this vector, I dot B with this vector, and I get 0.